Aloha and welcome back. In this video, we're going to be talking about asymmetric encryption. So we're in chapter 3, section 6, and we're going to be talking about a variety of things here. So let's go ahead and open up our textbook. And in our textbook, we're talking about asymmetric encryption. That's when we're using two different but mathematically related keys. And they're so one key is used for the encryption, one key is used for the decryption. So the asymmetric encryption, it's also known as public key encryption, and that's because you've got two related keys. One is a public key and one's a private key. So the owner of the key pair, they're gonna have the private key. They're gonna keep the private key and they're gonna use that for decrypting messages. So they hand out their public key to anybody that wants to send them an encrypted message. So they'll hand you the public key, and then you use that public key to encrypt the message, and then only they, with their private key, can decrypt it. And remember, these two keys, the public and the private key, they're mathematically related to each other. So unless you have that private key, which is extremely hard to get, you're not going to be able to decrypt it. And everybody has their own public and private key. One person's private key is not going to unlock, somebody else's messages. They're separate like that. So anyway, getting back to the explanations given here. So your message is going to be encrypted with the public key, and it can only be decrypted by the owner of the pair there. So keep that in mind. So they show an example here in the book with it. So the message sender obtains a message receiver's public key. So they send them the public key. They use that to encrypt it. So they're going to encrypt the plain text with it, and then they're going to send that over, and then they're going to decrypt it back to plain text using the private key. So just remember that the person that needs to read the message has the private key. Everybody else in the world can have the public key. And we've got some mix and match and some answers. Now we're going to get into the asymmetric algorithms. So something that's important here is the concept of one-way function. One-way function is a function that's easy to compute in one direction, but really difficult to compute going the opposite direction. So you can't undo it. It's not like when we were talking about symmetrical, where it goes both ways. It only goes one way. And then we have something called a trapdoor one-way function. A trapdoor one-way function is a function that's easy to compute in both directions, but only if you've got specific knowledge about the function's input or output. So the specific knowledge, in this case, it's called the trapdoor. So asymmetric algorithms are based on two classes of trapdoor one-way functions: integer factorization and discrete logarithm. And we're going to listen to this in just a minute. We've got some more on that. So we've got some more questions here. Now we get into our algorithms. So we've got three asymmetric encryption algorithms that are in use. So we've got RSA. RSA has a number of attributes here. So RSA, it uses the mathematical properties of prime numbers in generating public and private key pairs. So the security of it is based on the difficulty of factoring large prime numbers. In other words, getting the two numbers that are multiplied to get a large number. So encryption and decryption, it uses the using the RSA algorithm. It's slow and it's going to be computationally expensive. And it also, when you're talking about slow and computationally expensive, again, you're not going to be able to run this on legacy equipment, older equipment that can't handle the computational load. So the RSA algorithm is mostly used to set up a secure communication link between two parties for the purpose of exchanging a session key. So you're going to use this, you're going to go through all the trouble of setting that up, computing all that just for a short time to make that, to exchange that session key. So session key is a symmetric key that is used for the duration of a single communications session. So like if you're getting stuff from a website or something like that, for that communication session, you'll want to use that session key. And you're going to set up that exchange using the RSA algorithm. So RSA algorithms used in asymmetric encryption and digital signatures. So that's something to keep in mind. ElGamal, so the ElGamal algorithm, it uses discrete logarithms for generating public and private key pairs. The security of the ElGamal algorithm is based on the difficulty of solving discrete logarithms. So this encryption algorithm, it's probabilistic. And that means that a plain text may be encrypted in a different ciphertext. So the main disadvantage it has is the length of the ciphertext generated is going to be twice the length of the plain text. So it's going to take up a lot of space there. So this doubling of the ciphertext size makes the use of the algorithm inefficient, and it's going to not work very well in, like I said, resource limited devices and communications over low bandwidth networks. So if you have let's say around your school, I know some schools out there don't really have good Wi-Fi or good cellular reception. So in a low, in a situation where you've got, low bandwidth networks there, it's going to be difficult to actually use this. So where is it used? It's going to be used in asymmetric encryption and also digital signatures, just like RSA algorithm. So the last one we're going to talk about here is ECC. It's the elliptic curve cryptography. So elliptic curve cryptography algorithm, it uses elliptic curves for generating public and private key pairs. So an elliptic curve is the set of points that satisfy a specific mathematical equation. So the security of this algorithm, it's going to be based on the difficulty of solving elliptic curve discrete logarithm problems, or ECDLP. So ECC provides the same level of security as RSA that we talked about earlier, but the difference is it's going to be using smaller keys to do that. So ECC, it's more computationally more efficient than RSA, and it's used in resource-limited devices such as your mobile phones. So this algorithm, it's used for asymmetric encryption, digital signatures, and key exchange. So when you look at these three that we just talked about, they all are used in asymmetric encryption and digital signatures, but the last one, elliptical, the ECC algorithm, is used also in key exchange. And they have a nice chart here for us looking at the asymmetric algorithms. So it's got the computational efficiency, the power consumption. Power consumption is something we didn't talk about up above, but that's also important depending on the devices that you're using. And you can see the differences in the key sizes as well. So ECC, which is one of the better ones, computationally efficient, very efficient. It uses low power, and it's also the typical key size is going to be 160 versus 1024. So when you look at the basis of the security, the one RSA, we're talking about the factoring of two of prime numbers. Then we've got logarithms for the ElGamal, and for ECC, it's going to be the computing elliptic curves for discrete logarithms. So the last thing we're going to talk about is Diffie-Hellman. So looking here, asymmetric algorithms for that initial key establishment that we talked about. So asymmetric encryption, it's also used for establishing those symmetric keys. So we're using asymmetric to actually establish the symmetric key to do the exchange. So we've got something called the Diffie-Hellman, the DH algorithm, and this is a key exchange algorithm used for generating a shared symmetric key between two parties communicating over an insecure network. When we're talking about insecure networks, we're talking about like the internet. So then less about internal corporate networks, that type of thing. But the DH algorithm, the Diffie-Hellman, it can generate both a static key and an ephemeral key. So what's the difference between that? So your static key is a long-term key that's going to be used over an extended time period. The private key of a public private key pair, you can think of that as a static key because you're going to hold that for a long time. The ephemeral key, it's a key that's only going to be used for a single transaction. Ephemeral means fleeting for a short period of time. So you're really only going to use it for that one single transaction. Do not reuse. So, and you don't have to worry about that. The software does all this automatically, but you don't want to use an ephemeral key more than once. An ephemeral key is generated for each execution of a key establishment process. And the two methods that we use for this one is the Diffie-Hellman ephemeral, or which is the DHE or the EDH. The same words in each one. Ephemeral is the word, and Diffie-Hellman. So then the other one is going to be the ECC, so or the ECDHE, I guess, the elliptic curve Diffie-Hellman ephemeral, and that's going to use ephemeral keys that are generated using the elliptic curve cryptography that we talked about above. So the DHE and ECDHE, they provide something called perfect forward secrecy, and that's really important because perfect forward secrecy, it's a property of a key exchange algorithm which provides the assurance that a session key will not be compromised even if your static key, the long-term key that you have that was used to generate that session key, is compromised in the future. So let's say you used your static key to create this thing. Let's say you use your static key to create the session key. Well, that session key even though you've compromised the thing that you set it up with, that being compromised is not going to affect the security of your session key. So your session key is going to be safe. So that's the most important thing of that. So anyway, that's it for this section. A little bit of mix and match here. So go ahead and try that out. And that is it for section 3.6 on asymmetric encryption. If you've got any questions on this, reach out to me. Feel free to ask. Be happy to help you out. Aloha.